Hello and welcome. Today, we're exploring quantum computing and climate change. Let's hand over to Michelle to continue podcast.
You know, our planet's climate is one of the most complex systems we've ever tried to get our heads around. It's so complicated, in fact, that even our most powerful supercomputers are starting to hit their limits. But what if the answer wasn't just a faster computer, but a completely different kind of computer? And that really gets to the heart of the problem, doesn't it? Our normal, classical computers, they think in a very neat, orderly way. Zeros and ones, on and off. But the climate? It's anything but orderly. It's chaotic. It's a system where one tiny change can have massive, unpredictable effects down the line. So it makes you wonder, are we using the wrong tool for the job? So first up, let's really dig into why our best computers, the ones we have right now, are hitting this wall. I love this quote from a climate scientist because it just nails it. They said, climate models are beastly. And they are. I mean, think about it. They have to simulate everything all at once, from the chemistry happening way up in the atmosphere down to the currents in the deepest parts of the ocean. The math behind that is just, well, it's monstrous. To even try and handle this, our best supercomputers have to take shortcuts. They have to cut corners. So imagine trying to draw a map of a huge city, but you're only allowed to look at every 10th block. That's kind of what a coarse grid is. They also have to simplify really complex chemical reactions, making what are basically good enough guesses. The problem is, in a truly chaotic system like our climate, those tiny details they're skipping over, they matter a lot. A few molecules interacting in a specific way over the Pacific Ocean can literally influence weather patterns in Europe a week later. Classical computers just get bogged down trying to track all of those infinite possibilities.
And this is where the whole idea of quantum computing comes into play. This is the promise.
Now, this is a really crucial point. We're not just talking about building a faster version of what we already have. We're talking about a computer that fundamentally thinks in a different way. Its basic logic actually mirrors the complexity and the probability that we see in nature itself. And that makes it almost perfectly suited for tackling these chaotic problems.
So, what's the magic ingredient here? Well, it all comes down to something called a qubit. A normal computer bit is super simple. It's either a 0 or a 1. That's it. But a qubit is special. Thanks to a wild quantum principle called superposition, a qubit can be a 0, a 1, or, get this, both at the same time. And that ability to exist in multiple states at once is the source of its incredible power.
So what does this new kind of thinking actually unlock for us? Well, it means that instead of having to check possibilities one by one, a quantum computer can explore this huge, vast landscape of potential outcomes all at the same time. It can dive right into the messy, complicated reality of those quantum-level processes, the very things our current computers have to approximate, and it can simulate them directly. No more good enough guesses.
Okay, section 3. Let's get practical. How could this new tool actually make our climate model smarter? Let's start with one of the single biggest, thorniest questions in all of climate science. Clouds. How will clouds behave in a warmer world? Seriously, their behavior is incredibly difficult to predict, but it has a massive, massive impact on how much warming we can expect in the future.
Hello and welcome.
A quantum
Today,
computer
we're
could tackle this problem head-on.
Quantum
It could model
computing
the
and climate
formation of
change.
clouds
Let's hand over
right
to
down to the
Michelle to continue
microphysical level.
podcast.
You know, simulating that complex dance between water molecules and tiny aerosol particles that current computers have to simplify so much. If we could get that right, it would be a giant leap forward, dramatically reducing one of the biggest uncertainties we have in our climate forecasts.
And listen, this isn't just theory anymore. Scientists are actively designing specific quantum algorithms for very specific environmental jobs. For example, they're developing algorithms for quantum chemistry, like one called VQE, to perfectly simulate how pollutants like methane actually behave in the atmosphere. Other methods, like quantum Monte Carlo, could let us run millions of different what-if policy scenarios incredibly fast. This is applied science happening right now.
And the potential here, it just explodes beyond just weather models. Quantum computing could pretty much revolutionize environmental science as a whole. We're talking about everything from optimizing our renewable energy grids to designing brand new materials that can literally capture carbon right out of the air, to analyzing massive amounts of satellite data to understand our planet's ecosystems.
Okay, section 4.
We've talked up the promise. Now it's time for a little reality check. Because as incredible as all this sounds, quantum computing isn't a magic wand we can just wave tomorrow.
Yeah, the promise is absolutely immense, but the technical hurdles we have to clear to get there, they're just as massive.
First off, building a quantum computer is just incredibly hard. Those qubits we talked about, they're extremely fragile and finicky. The slightest vibration or change in temperature can create noise and completely ruin a calculation. On top of that, many of the most powerful algorithms we need, they still only exist on whiteboards. And even once the hardware is ready, we face this huge challenge of just getting these new machines to talk to our existing classical supercomputer. So this gives us a much more realistic roadmap. Right now, today, we're in the early stages, running small proof-of-concept tests on these noisy processors. The next step, in the near term, is probably building hybrid systems, where a quantum computer might tackle one very specific, very hard piece of a calculation and then feed that answer back to a classical machine. But the big prize? A full-scale, fault-tolerant quantum computer that can truly outperform our best supercomputers on these huge climate problems? Most experts agree that's still at least a decade away, maybe more.
So you might be thinking, okay, if it's that far away, why is there so much excitement? Why is all this investment happening right now? Well, it's because the potential payoff is enormous, and we have to lay the groundwork today. This is the ultimate goal. This is why it all matters. It's not just about scientific curiosity. When you get more accurate models, that leads to a much deeper understanding of critical risks, like climate tipping points. That deeper understanding translates directly into more precise, more timely warnings for things like hurricanes and floods, giving communities more time to prepare. And all of that lets us create smarter, more effective policies because they're based on far, far better data. And that really sums it up, doesn't it? This is exactly why major institutions like NASA and the Department of Energy are investing so heavily right now. They know that once the hardware finally matures, the scientific breakthroughs could happen very, very quickly. So the race is on to have the software and the algorithms ready for that day. So we'll leave you with this final thought to chew on. Could the strange, counterintuitive physics of the very smallest things in our universe hold the key to finally understanding the biggest picture of our home planet? It is a scientific quest absolutely worth watching.